Welcome to the third lecture of module 5 of mass transfer operation, and in this module we are discussing distillation operation. Before going to this lecture, let us have small recap of our previous lecture. In our previous lecture we have mainly discussed two important things. One is deviation from ideality and azeotrophs. Deviation from ideality and azeotrophs. The second important things we have considered is enthalpy concentration diagram. Now, in this lecture we will mostly concentrate on the flash distillation. Let us define what is flash distillation. So, flash distillation, sometimes called flash vaporization or equilibrium distillation, is a single stage separation technique by distillation. It is a single stage separation, and you can see the typical flash distillation unit shown over here. In this case, you have only one vessel, steel vessel, and you have fed into that, and you can get the distillate at the top as the bottom products. So, in this case what happens, a liquid mixture, that is a feed which is pumped at higher pressure through a heater. So, you have a heater over here, there is a pump before it. So, through the heater it is pumped, and in the heater it raises the temperature, and then temperature as well as enthalpy of the mixture, and then what happens, the mixture flows to the flash drum through a throttling valve. So, you have a throttling valve. So, once it is pumped through the heater, the temperature of the liquid mixture increases, and then through the throttling valve it goes to the flash drum. So, that is under reduced pressure. So, from high pressure side to the low pressure side, that is how the throttling is used over here. Because of this, the liquid gets partially vaporized, so which is entered into the chamber. Once the mixture enters the flash drum, the liquid and vapor separate. So, once the liquid at reduced pressure enters into the flash drum, so there is a separation between the liquid phase and the vapor phase. So, liquid comes down and vapor goes up. The vapor and liquid are allowed to reach equilibrium. So, we need to give enough space so that the vapor and liquid they disengage and then they reach equilibrium. So, vapor and liquid phases are separated and removed from the system. So, the liquid is removed as a bottom product and the vapor is removed as a top product called distillate. So, separation by flash vaporization are very common in industry. So, for example, petroleum refining, it is extensively used, this flash vaporization, or even when some other methods of separation is to be used, it is not uncommon to use pre-flash to reduce the load of the separation itself. So, generally if you look into any separation process or you need to have a complete distillation tower, before that you might have installed a pre-flash. In this way we can reduce huge load to the main tower, can be used in different separation pre-flash as a method for other separation process. When designing a flash drum, it is important to provide enough space in the drum for disengagement of the liquid and vapor. It requires enough space inside the drum, so that disengagement of liquid and vapor takes place, which is very much important. Drums can be designed as cyclone type. If it is cyclone type, what will happen? The liquid will goes to the wall on the cyclone and it falls down through the gravity, and then the vapor goes up. So, significant separation can be achieved. Now, consider a binary mixture of component A and B, two component system. We will discuss now the flash distillation of binary components. Now, the flow rates, composition and enthalpy of the feed, if we define the feed flow rate has a molar flow rate say F and its composition is XF. Similarly, its enthalpy would be HF. So, composition of the feed is given over here, and then flow rates, composition and enthalpy of the distillate, that is coming at the top product. So, which is given over here, the distillate molar rate flow rate is D, it is a vapor. So, vapor composition is YD and its enthalpy is HD. Then we have bottom products, the flow rates, composition and enthalpy of the bottom products, which is shown over here, where you have W is the molar flow rate of the liquid which is coming out as a bottom product. Its composition of the solute is XW, that is the lighter components, and its enthalpy is HW. So, condition for a particular solute is given at feed, distillate and the bottoms. Now, let Q be the rate of supply of heat to the heat exchanger. So, if we supply the heat over here to preheat the feed at a particular temperature, we need to supply some heat to this heat exchanger. Let it be Q. Now, we do the following assumptions: no heat losses to the surrounding. So, assuming that it is insulated systems, these things, and there is no heat loss to the surrounding. So, insulated system. Ideal gas behavior for the vapor. So, vapor which will generate over here should be ideal in nature, and perfect mixing. So, mixing of the between the vapor and liquid, there is perfect mixing. So, if we consider these three assumptions, and then if we do the material and energy balance for a steady state flash vaporization unit, first we will do the material balance. So, feed is F mole per, so per unit time, and then you have a distillate flow rate which is D, and you have a bottom flow rate of W. So, total material balance would be F is equal to, so entering into the flash drum over here is F, and out from the column is this 2. So, rate of moles in would be equal to rate of moles out. So, if you do that, F would be equal to D plus W. Let us say this is equation 1. Now, if we do the component balance, so component we have a over here which is more volatile components. So, having the total flow rate F and its composition of the more volatile component is ZF. So, F ZF would be equal to distillate flow rate into mole fractions of the solute is YD in the distillate plus W, which is the bottom flow rate, into the mole fractions in the liquid, which is XW. So, F ZF would be equal to DYD plus WXW. So, this is equation 2. Now, let us do the energy balance. In this case, you can see with the feed has the enthalpy of HF. So, F into HF plus no heat which is supplied to the heater, which is Q. So, plus Q would be equal to enthalpy of H d d into H d, which is for the top product, and then for the bottoms W H w. Since we have considered there is no heat loss to the surroundings, so the energy balance should be valid like this. Now, if we use the equation 2 and 1, the equation 1 is this, the total material balance, and equation 2 is the component balance, which is FZF is equal to dYd plus WXW. Now, using these two equation, if we just do the rearrangement, in place of F, if we substitute d plus W, we will have d plus W into ZF would be equal to dYd plus WXW. From this we can write d into ZF minus YD would be equal to W into XW minus ZF. Just multiply ZF with these two terms and then do the rearrangement. So, you will obtain this. Now, if we just simplify it again from this equation, you will get minus W by d would be equal to YD minus ZF divided by XW minus ZF. Similarly, using equation 3 and 1, we have F HF plus Q, that is the energy balance equation, is equal to D HD plus W HW, that is equation 3 energy balance equation, and equation 1 which is total material balance equation, F would be equal to D plus W. Now, if we substitute this D over here, F we can write D is equal to F minus W. Now, substituting this over here, we would obtain F HF plus Q would be equal to F minus W HD plus W HW. Now, if we just do the rearrangement, that is F HF plus Q would be equal to F minus W HD plus W HW. So, from here we can write F HD minus W HD plus W HW. So, if we rearrange F HF minus F HD plus Q would be equal to W HW minus W HD. So, from here we can write F into HF minus HD plus Q would be equal to W HW minus HD. Now, further rearrangement, it would be HF minus HD plus Q by F would be equal to W by F into HW minus HD. So, from here we can write W by F into HD minus HW would be equal to HD minus HF plus Q by F. Now, if we just write the same equation again, F HF plus Q would be equal to D HD plus W HW. So, say this is equation 5. Now, the total material balance F is equal to D plus W. So, W we can write here F minus D. From this we can write D HD plus F minus D. So, in place of W we substitute F minus D. So, we will have F minus D HW. So, we can write this thing as D HD plus F HW minus D HW. So, here if we do rearrangement F HF minus F HW plus Q would be equal to D HD minus D HW. Then we can write F into HF minus HW plus Q would be equal to D into HD minus HW, and again we can write HF minus HW plus Q by F would be D by F HD minus HW. So, from here we can write D by F into HW minus HD would be equal to HW minus HF plus Q by F. So, say this is equation 6. Now, if we divide 5 by 6, so divide 5 by equation 6. So, you will essentially obtain minus W by D would be equal to HD minus HF plus Q by F divided by HW minus HF plus Q by F. Say this is equation 7. So, this is we have done, this is equation 5, this is equation 6, and then we divided and we obtained equation 7. So, this is equation 7 which we have obtained. Now, if we look into the HXY diagram, so which is shown over here, the equation 7 represents the equation of straight line through points D, which is over here, is HD YD. So, you could see this is YD. So, if you go straight to the XY curve, that is mole fraction curve, so it will go to the 45 degree diagonal and then this is YD. So, point D represents XD, HD, YD on the enthalpy concentration diagram, and W which is over here it represents HW and corresponding mole fractions is XW here, and also HF plus Q by F. So, which is this part. So, HF plus Q by F, which is shown over here, which is on the point between D and W. This is the enthalpy of that point, and ZF, that is the fit condition, which is given over here. So, if you come down here from here, and so you have HF, and then you can come down to the 45-degree diagonal, you can have ZF. So, it is on the 45-degree diagonal and having the composition ZF, ZF. Now, the slope of the operating line are minus W by D, which is shown over here, and the other slope for this line is basically YD minus ZF, which is YD minus ZF divided by XW minus ZF. Okay. So, which will be negative again, because ZF is more than XW. If the effluent streams are in equilibrium, the product D dash and W dash, which is shown over here, if they are in equilibrium, you can see that you come down from this line, from this point to the curve. This is the intersection point with this slope minus W by D. It intersects the equilibrium line at this point. So, the product, if they are in equilibrium, so you will obtain D dash and W dash. So, this will represent is the tie line. So, we will consider a different arrangement of the steady state model. These will be useful in some of the solution methods. Let the fraction vaporized of the feed as F. So, it is not completely vaporized, and consider that it is fraction of the feed is vaporized, and that fraction is defined as F is equal to D by F. So, D is the distillate and F is the feed. Now, if we write the material balance, we can write from the overall material balance whatever we have written. So, 1 would be equal to D by F plus W by F. So, basically F is equal to D plus W. So, if we divide both sides with F, so this would be 1 would be equal to D by F plus W by F. So, and this D by F we have defined as F, that is fraction vaporized, plus W by F. If we just rearrange this equation, so it will be W by F would be equal to 1 minus F. So, this is equation 8. From the earlier component balance, we can write, that is F ZF is equal to D YD plus W XW. So, this is the balance equation. Now, if we divide both sides by F, that is the feed, then it would be ZF would be equal to D by F YD plus W by F XW, which would be equal to F, this is the fraction vaporized F D by F, F YD plus W by F we have calculated is 1 minus F. So, plus 1 minus F XW. So, this is equation 9. Now, there are two unknown in equation 9, one is YD and XW. So, we need a second equation between these two unknowns which would be available, and so that we can use this equation to calculate the enthalpy concentration diagram and solve the problem. So, to do that there are two options available with us. One is equilibrium curve. If equilibrium data is available, then we will have equilibrium curve, or it can be based on the relative volatility equation, that is alpha. So, either of these two should be available to relate between these two compositions YD and XW. Now, for a binary system, as we have already discussed, alpha AB would be equal to YA by XA divided by YB by XB. So, XB would be equal to 1 minus XA and YB would be equal to 1 minus YA. So, the above equation can be rearranged to get Y would be equal to alpha x divided by 1 plus alpha minus 1 into x. So, this is the relative volatility equations. Knowing the values of alpha, and we can have guess any values of x and we can find out y. So, this equation can be used to find out the x y relation or the equilibrium curve, so that the problem can be solved. Now, the flash distillation unit, the calculation procedures are very simple. To solve a flash distillation problem, one simultaneously solves the operating and equilibrium equation. So, operating curve equations also we need, at the same time we need the equilibrium equations. Flash calculation can be solved directly, but usually required some iterative solutions. Graphical techniques are also common for calculation of the flash calculation. Often the choice of technique depends on the available form of the equilibrium relationships. So, depending on the data available or the relationship available, the choice of the techniques will depend whether it will be analytically or we should go for graphically. Now, let us take an example to find out vapor and liquid composition which is coming out from a flash chamber. Now, a mixture of liquid containing 50 mole percent N-hexane and 50 mole percent N-heptane is subjected to a flash distillation at 1 atmosphere total pressure and 40 degree centigrade temperature to vaporize 50 mole percent of the feed. So, 50% is vaporized. The relative volatility of N-hexane in the mixture is 2.36. Now, we need to calculate the composition of the vapor and liquid leaving the flash chamber considering an equilibrium stage. The vapor pressure for this system can be obtained from the following Antoine equation. So, this is the equation, Antoine equation, which is similar the problem we have taken, which we have discussed in the first lecture. The same example, that is N-hexane and N-heptane mixture. The boiling points and their constant values for this Antoine equation is given over here, which is in this table. So, for N-heptane and N-hexane. Now, the data which is given XF is 0.5, 50%. So, 50 mole percent, and for the basis assume that feed is 100 mole. So, the distillate would be 50 mole because 50 mole percent N-hexane, and then bottom W would be 50 mole. So, minus W by D, that is the slope, would be 50 divided by 50. So, it would be minus 1. So, slope is minus 1. Now, relative volatility is given alpha. So, which is 2.36, and this is the relation between the vapor and liquid composition, that is relative volatility equation. So, once we know alpha, we can get the x y data. So, we can plot the equilibrium curve. So, data using this alpha values, and x varies from 0 to 1 and y varies from 0 to 1. So, we can calculate the x and y values and we can plot the x y diagram. So, you can see over here the x y diagram are shown over here. First we need to draw the x y diagram, then as the bubble point, boiling point are given for both the components, and their Antoine equation is given to calculate the vapor pressure. So, either from there or from here we can plot the Txy diagram, that dew point curve and then bubble point curve we can draw over here as shown, because it is the same examples which we have taken during the first lecture. So, you can see the same figure you can obtain over here. Now, we have feed is 0.5, XF is 0.5, is 50 mole percent of N hexane, and slope we have calculated which is -1. Now, with ZF is equal to 0.5, we can locate a point here. So, once we get the point on the x axis of xy curve, then we can just go vertically and locate on the 45-degree diagonal of the xy diagram. This point is known, we obtained, and so we can identify this point, and which corresponds to ZF is equal to 0.5. Now, we can plot with this slope minus W by D is -1. From this point, slope of this line is equal to -1. So, with -1 slope from this point we can plot this line which intersects the equilibrium curve at this location. So, we can locate the intersection point between this line with that slope and the intersection point on the equilibrium curve, and then go horizontally to the y axis to calculate at this point you will get YD. So, here it is YD. So, you can calculate YD which is about 0.65 mole fraction of hexane. Now, you can get the composition of the distillate which is YD. Now, what would be the bottom composition of the N-hexane? So, now from this point you just go vertically down to the x axis, you would obtain that is XW. So, which is over here. So, you will get XW is about 0.37. So, once you calculate YD and XW, now we need to calculate the temperature of the mixture at bubble point temperature. So, to calculate the bubble point temperature, what we need to do? We need to draw a vertical line from this intersection point and which will meet the bubble point curve at this location over here. So, which is shown over here. So, which intersect the bubble point curve here. From this intersection point between the bubble point curve and the vertical line drawn over here, you go horizontally from this point, move horizontally to temperature axis and to get the bubble point temperature which will meet at this location, you would obtain is bubble point temperature T, which is about 83 degree centigrade temperature. So, this way we can solve the flash distillation problem for a binary mixture. So, with this I conclude this lecture. Thank you for attending this lecture and patience hearing, and we will continue our discussion on distillation operation in the next class.